session of today's talks. So we invite Professor Pei-Ming Ho from National Taiwan University for giving us a lecture about dynamical black holes and information loss paradox. So this is the part one of his talk. So please start.
Okay, thank you. I'd like to thank the organizers for inviting me to give a review and also mention my recent research about the topic of information loss paradox. So I'll give 3 talks, and in the first talk, I'll talk about what the information loss paradox is about, the key point of the paradox, maybe the more traditional view where the paradox is coming from, and what are the assumptions behind the paradox, and if there is a resolution, what the resolution should look like. And in the second lecture, I'll explain the conventional model of black holes, which is the reason, the setting in which you have the paradox. If you choose a different model for black holes, then you may not have the paradox. But I'll explain some details about the conventional model and why people believed that this model is correct. That will be the second lecture. And during the second lecture, maybe you would like to take a challenge to see what is missing, what people didn't check carefully. Is there any loophole in their arguments to believe in the conventional model? And then in the last lecture, I'll mention some of my recent works and point out directions in which the information loss paradox may be resolved. Okay, so for the first lecture, somehow the slide doesn't change. Let me see. Oh, okay. In the first lecture, I'll review the information loss paradox. So here I have a Penrose diagram. Penrose diagrams are just poorly drawn diagrams of the space-time. So the whole space-time is supposed to be compactified within this finite domain. So the notion of distance is completely ignored, but the only thing you can trust is that lines at 45 degrees are light-like. So lines that more vertically pointed would be time-like and otherwise space-like. So this is the conventional picture Hawking had for evaporating black hole. So you have this curve which represents the surface of the collapsing matter. You have this red line for the singularity at the origin. And then the end of the singularity marks the endpoint of the event horizon. So the event horizon is extended from the endpoint of the singularity backward in time at 45 degrees. And also here I plotted the dot curve, which is the trapping horizon or event horizon. And then you have the Hawking radiation. So the standard story is that Hawking radiation takes away energy of the black hole. So the black hole is shrinked and then eventually it disappears. So afterwards you get the flat Minkowski space again. And the question is where the information goes. In the conventional model, the idea is that if you have a very large black hole, since the gravity around the horizon is inversely proportional to the mass of the black hole, so you can have an arbitrarily small gravity around the horizon for a very large black hole. So we can imagine that there is a huge black hole so large that the gravity around the horizon is actually smaller, weaker than any apparatus we have can detect. So we could be crossing the horizon right now at this moment. And we don't know it because the event horizon is just a global concept of the geometry. we don't know where it is until there's this singularity. And also the notion of trapping horizon also depends on your choice of the foliation. So it's also not a local geometric concept. So we could be just crossing the horizon right now, but then here comes the paradox. That is, we don't feel like everything is probed by something. So like the secrets in your head or the passcode to your bank account, if you put it in a safe, you don't see high energy photons penetrating the safe and to bring out the information of the password you wrote on a piece of paper in the safe. But somehow all these information will be accessible to aliens far away. So in standard model or in any low energy effective theory, we can imagine there is no such mechanism to bring out all the information, I mean, including the information of the quantum state of a quark in a proton in an atom in your body. All these information without being probed by any high energy particles will be accessible at somewhere else. So we simply cannot imagine how low energy effective theory can provide a mechanism to transfer all these information in a region like our surroundings to some radiation. So that's the question. So to repeat again, because this is a very important point, you can have a black hole that is arbitrarily large. So that surface gravity, the gravity at the horizon is arbitrarily small, much smaller than the gravity on Earth, for example. So there's no reason to suspect that the low energy effective theory, like standard model, would certainly be invalid. It should be a very good model to describe the situation. However, the information of everything of the collapsed matter will become available in Hawking radiation. This transfer of information cannot be described by any mechanism in the standard model. If we can accept this kind of information transfer, maybe astrology is not so ridiculous. We can believe in anything, I guess. Of course, people may say that there's a string effect because according to string theory, we have many evidences that information would be preserved. Unitarity would be intact. However, there is a very important principle, the decoupling principle, which says that if there is no high energy events, the high energy theory should be irrelevant. The low energy effective theory should be sufficient to describe the phenomena. So unless there is some Planckian scale or very high energy events, the standard model should be working. And the standard model is unitary, so whatever you can describe with standard model would be automatically unitary. So this is why even though we believe in string theory, and string theory supposedly would resolve the information loss paradox, this is still an important question to ask because it has to do with when and where we can still trust the low energy effective theory. And if we do not know when we can trust effective theory, basically we cannot trust physics anymore because all the time we are using low energy effective theory to make predictions. So are there any questions?
So may I interrupt you this occasion? So
Yes.
in your Penrose diagram, in fact, so there is a singularity and there is a horizontal, so vertical line, which is attached to the end of this singularity line.
Right.
No, I mean the right one. Yeah, there. So well, what happens around there?
You mean actually what happens there?
Yeah, the low energy description actually still we can believe in it.
No, yeah, we cannot believe the low energy effective theory here but we can believe the low energy effective theory down here.
Yes.
At the early stage of the evaporation. So yes, I will be focusing on the early stage of the evaporation. But the information would have to come out already, you know, well before the last point of evaporation. You would already have a lot of information coming out. For example, maybe 9/10 of the mass of the black hole is already evaporated. So a lot of the information is already out there, but 1/10 of the black hole can still be arbitrarily large. So the curvature is still small and you may not still see anything high energy and low energy effective theory should still be valid. It should already tell you how information is transferred.
Oh, I see. So, yeah, maybe this is a stupid question, but what is the sense of considering 1/10? For example, if at the very last moment of evaporation of black hole, all the information is still there, and then low energy description is broken there, and then suddenly with some unknown mechanism, all the information will be revealed.
Right.
And,
right. So that's a possibility. So that's, I think, similar to what people call the remnant situation.
Yes.
But since that scenario is not compatible with holographic principle, so I thought at this, you know,
I see.
for the holographic workshop, I don't have to consider that possibility.
I see.
But so there are several arguments against remnant. One is that the holographic principle, the Bekenstein-Hawking entropy should tell you how much information you can keep inside the black hole. So if you have a tiny black hole, but with an arbitrarily large entropy inside, it's not allowed. And also, if you have a remnant with an arbitrarily large internal degrees of freedom, then this would also put low energy effective theory in danger, because you can imagine internal loops in Feynman diagrams in which, even though the remnant as a particle may be very heavy, but there is infinite internal space to integrate over. So your Feynman diagram would certainly be totally different with such remnant particles. I am assuming that people here do not accept that possibility. Yes, but you are right. That's a possibility, but here mostly I'm assuming people believe that information will come out as Hawking radiation. Yeah, thank you for.
Thank you very much.
Right, so so that's why we care about information loss paradox, because it's related to how or whether we can still trust physics in predictions. Yes, as you said, there would be a high energy event around the endpoint of the evaporation. But actually the singularity here simply marks the point where low energy effective theory is invalid. So once you have a UV theory, like string theory, the singularity would be resolved into a region of high curvature, like this one. And then there would be no event horizon, because the event horizon is defined as the endpoint of the singularity extrapolated backward. You would still have the trapping horizon once you pick a foliation. For spherically symmetric configurations, there is a natural way of picking the foliation, but still that's assuming that you have a complete knowledge of the whole configuration. So when we are passing through the horizon right now, for example, we don't really know where is the horizon or where is the central point where you have the spherical symmetry. So none of these things should play an important role in resolving the information loss paradox. Although the traveling horizon could be a useful reference point when you describe the geometry. But anyway, so you have this kind of picture. We don't really know what happens around the endpoint of evaporation. So we will be focusing on the early stage of the evaporation. And so during the early stage, when you already have Hawking radiation bringing out information of the collapsed matter, there must be something unusual happening around the horizon. So in the review paper by Mathur, he said that there must be some drama at the horizon. You must have something to tell you that the low energy effective theory breaks down in order to have the opportunity of transferring information to Hawking radiation. So to find where this drama is or how it appears would be the most important point in resolving the information loss paradox. So now I'd like to give you 3 more arguments for why we need high energy events around the horizon to resolve the information loss paradox.
Excuse me?
Yes.
Yeah. So when you say high energy, so it may depend on observer, and so when you claim it's high energy, so for what in a sense? So for what observer you in mind?
Yes, very good. So I'm going to need an invariant high energy quantity, not like you know, after Lorentz boost it becomes high energy. So I need an invariant quantity.
Is that mean for which observer?
So for all
it
observers,
doesn't depend on all observers.
That's right. It doesn't depend on observer. Observer independent high energy. That's what I need. Yeah. So for example, people know that the Hawking radiation at distance has a low frequency, but if you extrapolate it back to the horizon, it has a very high energy, but that doesn't count because that is energy that you can Lorentz boost down to a very small energy. So that doesn't count. So for example, we are using standard model to compute scattering processes between very high energy particles in the cosmic rays and particles on Earth. Now those particles in the cosmic rays, they have very high energies, energies well above the validity of the standard model. But the center of mass energy of the scattering between these ultra high energy particles in cosmic rays and particles on Earth could still be well below the validity of standard model. So we can use standard model to predict what's happening. Yeah. So here also, we need some invariant quantity independent of the observer to be high energy.
So are you showing its expression?
Sorry?
Sorry. So you are so can you show it in your? Sorry. Are you going to tell us about this quantity?
Yes.
Okay. Thanks.
Yeah, I will talk about it, but only in the last lecture. So you have to survive till the end.
Okay.
But now I point out the necessity of such a high energy event. Right. So the first argument goes like this. If you have a low energy effective theory in which you have some global symmetries and associated charge conservation, for example, the baryon number, then you can pick the particle with the largest charge over mass ratio. And then you can imagine taking a large number, n of these particles, and let them collapse to make a black hole. And so during the collapse, every particle has gravitational potential energy. And so in the end, the black hole has a total mass that is smaller than n times the mass of each particle. because of the gravitational energy. You know, during they fall, they maybe radiate some energy away. And then you have Hawking radiation. So the mass of the black hole is reduced from m to m minus delta m. Now the total charge of the whole universe is now the charge inside the black hole, which is this portion of the total charge. So m under m minus delta m, this is the fraction of mass remaining in the black hole. So we assume that the same fraction of charge remains in the black hole. And then you have this mass going out to infinity as Hawking radiation, and they carry this much charge at maximum. But the sum is actually smaller than the initial charge because of this inequality, m less than nm. So you would have charge conservation violation. So your low energy effective theory, which is allowed to have some global symmetry and associated charge, you inevitably would find charge violation. So there must be some high energy events breaking this global symmetry. People have noticed this long time ago. So from here, we also conclude that string theory or a UV theory of gravity would necessarily have no global symmetry. All the symmetries must be local, so that when they radiate, when they approach to the extremal black hole, they stop radiating. That would solve this problem of charge conservation violation. So this is the first argument. The second argument is similar, but the emphasis is different. So consider two types of particles, A and B. They have the same mass and same charge. And we let them to collapse in different profiles. Sorry, in the same profile. In the same profile in the sense that they have the same gravitational field. So you can have the same gravitational field, but the matter is composed of different particles at your choice. Now the Hawking radiation would be exactly the same because Hawking radiation is determined largely by the gravitational effect. We will review how Hawking radiation is generated, but the standard calculation is that it's mostly determined by gravity. Interactions can have some effect. People have studied that part, but the effect is not enough to bring out all the information. Anyway, you can have a global symmetry such that the interaction is the same as well. So information about whether it's particle A or particle B collapsing, this information is lost. So again, we need high energy interaction to distinguish A and B in the UV theory. So this tells you that even pure states contain information. You can have pure state of particle A or pure state of particle B collapsing. And also it tells you that the supertranslation charges of gravity is not enough because you can have additional information that is beyond gravitational effect. So the last argument, also we consider two similar things collapsing. Here we consider two books of the same weight and size, but different story. Now, to tell the difference between the two books, you need some particles with sufficiently short wavelength to distinguish the letters printed on the two books. However, if the curvature radius of this neighborhood is much larger than the size of the printed letters, then you cannot tell the difference between the two books. So if there is no high energy particles around the horizon, you can't tell the difference between different objects falling in as long as they have the same gravitational effect. So here, so all the arguments are similar, but I emphasize on different aspects, like the size of the information and the wavelength, or in the previous examples, the conserved charges, and so on. So the information loss paradox is really important because it's about fundamental principles in conflict. People believe in the uneventful horizon assumption in conventional model mostly because of the equivalence principle. Now, the equivalence principle says that if you have a space-time geometry with curvature invariance, all of the characteristic length scale A for the Schwarzschild black hole, A would be the Schwarzschild radius. In this case, when you are in free fall, you do not expect high energy events with energy much larger than 1/A. This is the equivalence principle. So the equivalence principle is saying that if you are in free fall, then you should not feel different from floating in space, in flat Minkowski space. But you have a curvature A, length scale A, so we should be restricted to experiments done in a region much smaller than A. So if you are in a lab, the size of the lab is much smaller than A, then all the outcomes of your experiments in the lab should be the same as done in a spaceship floating in space, in Minkowski space. Now, if you are in Minkowski space, floating in space, you look at a vacuum, there would not be high energy particles popping out of the vacuum. So similarly, if you are free falling, you should not expect vacuum to pop out high energy particles, at least not beyond this characteristic length scale. So for a very large black hole, this energy is very low. So it's not enough to take away the information of the collapsed matter. On the other hand, string theory cannot help you because of the decoupling principle. So you have a conflict between the equivalence principle and the decoupling principle. Sorry, I'm missing the letter E here. So either one of the two fails, and the question is which one has to fail. It seems to be the situation. In the end, this may not be the actual conclusion, but right now it looks like this is the situation, or at least this is how people have presented the information loss paradox. Is there any question? So if we have a resolution, what would be the minimal thing in the resolution so that we can say, oh, information loss paradox is not really so much a direct conflict, or it's something that is acceptable, like burning coal. If you're burning a piece of coal, you cannot really describe the process precisely in theory, but you don't worry about it. So to not worry about the information in black hole evaporation, the minimal resolution required is the following. First of all, I suppose we do not want to give up decoupling principle, because if we give up decoupling principle, then you cannot trust anything you derived in low energy effective theory, including Hawking radiation. So basically you can just say that, oh, maybe I don't have Hawking radiation, and then I have just classical black holes, so there's no information loss. So giving up decoupling principle is like giving up everything. So that must be kept. So we can give up equivalence principle a little bit, but how much is needed to be given up? So the minimal resolution, I think, is that if we can show that whenever there is Hawking radiation, then there is no uneventful horizon. So basically the conflict is between Hawking radiation and uneventful horizon. When you have Hawking radiation, it has to take out information and it has to imply high energy events around the horizon. So you cannot have an eventful horizon. So the goal would be to show that whenever you have Hawking radiation together with effective field theory, without string theory, you would have high energy events. And therefore, this implies that equivalence principle, as people have described, is violated. Is there any question? So this looks very much like the firewall proposal. So in the firewall paper, they listed several postulates, essentially the same postulates people usually make. And also they propose that the uneventful horizon is the postulate that should be given up if you want to preserve information. This is the least dramatic way of resolving the paradox. Now, there are many papers in which they claim that the arguments of the firewall proposal can be circumvented to preserve information, but this does not imply that firewall will not happen. So our attitude below would be slightly different. We would not be concerned with whether information will be preserved. We would just try to understand in detail the dynamical process of black hole evaporation. So we just study the dynamical process of black hole evaporation in the effective theory and check carefully whether there will be high energy events. If there will be high energy events, we will be happy. We will have to say, well, people in the past have missed some calculation they didn't do. If we cannot find any high energy events, then it is what it is. We cannot say anything, then we are just in deep trouble and we have to maybe invent something more dramatic, more radical. But the first step would be to look carefully into the low energy effective theory description without worrying about information loss paradox, if we trust effective field theory. Now, there are many works on information loss paradox that focus on the problem of counting the information in the black hole and in the Hawking radiation, like problems about the entropy or worrying about no cloning theorem. I'm sorry, this list of references is clearly not complete, but I just want to mention what is missing in this approach. Well, usually what people say is that if you have unitarity in the process of black hole formation and evaporation, then if you start with a pure state, after gravitational collapse and radiation, in the end, you should also get back to a pure state. So the entropy of the initial state is 0, and the entropy of the final state is also 0. But this is actually not enough to guarantee unitarity, because you can have state A and state B, both evolving to the same state. In both cases, the left-hand side and right-hand side are both pure states and entropy vanishes, but clearly, if your theory predicts both lines, then this theory is not unitary. So still, you need high energy events to distinguish. So pure state to pure state is not sufficient to guarantee unitarity. You need high energy events. And once you have high energy events, then these high energy events would contribute to the energy momentum tensor in your Einstein equation, and it would change the geometry. So if your counting of entropy depends on the background geometry, the counting would not be reliable anymore. So it should be a first priority to make sure that the geometry is correct. For that purpose, you need to make sure that or the high energy events are located, if there are any.
I have a question. Sorry.
Yes.
In the paper from Pennington, Schenker, Stanford, and Young, besides, I mean, okay, it's in a toy model, so that's, but besides computing the entropy, they also give a prescription to extract the information, doing
Right.
very complicated operations on the Hawking radiation, and supposedly they have this PETS map picture that allows you to extract it, that somehow creates some wormhole that lets you extract the information.
Right.
I was just wondering what's your opinion on that, because that's maybe some calculation that goes a little beyond just computing the entropy.
That's right. That's right. But there, firstly, they assume the geometry to be given by the conventional model. I mean, apart from the wormholes, and the wormholes are something that's not already predicted by standard model, right? So that is not something predicted by the low energy effective theory. So they have already gone to the more radical approach. So of course, if you introduce new things into your theory, then you can have a more concrete model. Yes, more than counting information. I'm sorry that maybe my comment earlier was maybe misleading, but I was assuming that we are restricted to the low energy effective theory to try to resolve the paradox in the low energy effective theory.
I see. No, that's fine. I just wanted to. I didn't mean to complain. I just wanted to know what your opinion on that was.
Yes. Yes. Thank you.
Thank you.
So, so it's very important to know what people have done, why people believed in the uneventful horizon hypothesis. What is the conventional model? So from now on, I'll describe what is the conventional model, what are the assumptions, and then in the next lecture, I will go over more details in the model. So here, the basic assumptions of the conventional model are the following. So first, we assume that the semi-classical Einstein equation is correct. And there are people who believe that this is not correct. But as we were saying, if we could be passing through the horizon right now, we know that in our neighborhood, the Einstein equation is pretty much valid. So we do not have a good reason to suspect that this is no longer correct. And then this next assumption is that for quantum matter, for the matter collapsing into the black hole, we can use low energy effective quantum field theory to describe this matter. So this allows us to do some calculation and tell us that there will be Hawking radiation. So apparently we almost always have to make these two assumptions. And then we also assume that the classical solution is approximately correct. Namely, if you set the right-hand side to 0 for vacuum, I mean outside the collapsing matter, the geometry outside the collapsing matter should be approximately described by the classical solution for which the right-hand side would be 0 in vacuum, because the quantum correction, the quantum effect is usually very small. If you consider an H-bar expansion, you can consider the problem prohibitively in H-bar. So here I wrote Schwarzschild approximation, but more generally, I mean classical approximation, but we will be focusing on spherically symmetric cases. And so we will just need Schwarzschild. And finally, we assume uneventful horizon, that the horizon is in a quantum state of vacuum for free-falling observers. For free-falling observers, due to equivalence principle, they shouldn't see a lot of high energy particles popping out of the horizon. So the first two assumptions are about the theory, the theoretical framework we use to do computations. And the next two assumptions are about this particular configuration of the black hole, the quantum state of the black hole. And with these assumptions, you can do usual calculations you do in theoretical physics, analyze how the black hole would evolve with time. So it's a pretty well-defined question. And then the task is to understand in detail the dynamical process of black hole formation and evaporation, and to check whether there is a high energy event. But we are not using information loss paradox to introduce high energy events by hand or to introduce anything beyond low energy effective theory by hand. So now I'll talk about these different assumptions a little bit more. So first, the effective theory and then the configuration. So the first two assumptions about semi-classical Einstein equation and low energy effective quantum field theory for the matter field, together I'll refer to them as the effective field theory, the theory we use for our neighborhood of space-time, and should be sufficient according to the conventional model. So now the semi-classical Einstein equation, once you give me the energy momentum tensor on the right-hand side, you can solve it and find the magic. On the other hand, the right-hand side depends on the background geometry. So in principle, you should solve two equations at the same time. One tells you how gravity is determined by energy momentum tensor, the other telling you how energy momentum tensor for the vacuum is determined by the metric. Now, this is too hard to solve simultaneously. So what people usually do is to do it perturbatively. So you first make a guess about the background geometry metric. And then in this background, you quantize your matter field. And then you can compute the energy momentum tensor for a certain quantum state, say the vacuum state for free-falling observers. This part is usually very hard if you want to do a first principle calculation. So sometimes we use other ways to compute it. I'll describe about that in the next lecture. But basically, you're supposed to give a good guess about this energy momentum tensor for a given background. And then you can plug it into the right-hand side of this Einstein equation and solve it again and check whether the initial guess is a good guess. If there is a small deviation, you can include that deviation and repeat the process. You reiterate. After several iterations, if you find the solution converges, then you are happy and you get a consistent solution. So this is one way to proceed, the usual way we do in theoretical physics. And so that's the way people did also. So I'll talk about how this was done in the conventional model in the old days. Now, on the other hand, there are other questions you may ask. For example, there would be higher derivatives involved in these equations. So in principle, there could be more than one solutions. There could be many solutions. And you may ask whether the particular solution you get from a particular initial guess metric, maybe that's not a generic solution. Maybe that's not, maybe that happened to be a fine-tuned solution. And maybe generic solutions would have high energy events. So that's one possibility. And also another point to pay special attention to is whether this energy momentum tensor could be estimated accurately. And does it play an important role? Its back reaction to the geometry, if it's very different from the classical solution, then the assumption of a conventional model is incorrect. Then the other two assumptions are about the configuration. So we have this assumption about Schwarzschild approximation. We assume that
I have a
we
question.
can, yes.
Sorry to interrupt. So in the previous slide, maybe in your second lecture, you may explain, but so what is the consistency with H bar expansion for both sides of this equation?
Yes, that's right. So that's actually what I'll just tell you about in a few slides. Yes, thank you. Actually, it's right in this slide. So we assume that we can start with this perturbative expansion at the 0th order from the classical solution. And then you have quantum correction proportional to h bar. With the Newton constant, you can rewrite it as Planck length squared. So you can think of the expansion in h bar as an expansion in powers of Planck length over Schwarzschild radius squared. So that is the expansion parameter. So certainly for a reasonable size black hole, this number is extremely small. However, if we look at the Schwarzschild metric, where the Schwarzschild radius is proportional to the mass, you have these factors like 1 minus a over r here and also here. Due to these factors, when r minus a is of order Planck length squared over a, you plug this in here, you see that you get from here and here a factor of Planck length over a squared. So that means that on the left-hand side of the Einstein equation, you would also get factors of these. And you can also get inverse of this factor like here. So saying that the right-hand side has an expansion in this parameter actually does not guarantee that this is a good perturbative expansion, because on the left-hand side, you also have factors of that. So a priori, you cannot immediately be sure that this is a good expansion. You really have to solve it explicitly. And actually, we will see that it's actually sensitive to the state you are considering. For the classical Schwarzschild solution, you actually do not have to carefully distinguish a static permanent black hole from a collapsing gravitational collapse black hole formation. But if you consider the quantum effect, actually you would get totally different results. In one case, the classical approximation is good. In the other case, the classical approximation is bad around this neighborhood in this regime. So it's not a clear, it's not clearly a good approximation, perturbative expansion. So like here, we have often in discussions about black hole, this picture, the Penrose diagram for a maximally extended Schwarzschild solution. This is of course not the physical process we want to talk about, because we don't have a white hole in the infinite past. Usually the physical scenario is to have a nearly Minkowski space in the early time when everything has very low density. And then through a gravitational collapse, you have something more like a Schwarzschild solution. So with different initial condition, you get different quantum states. And the quantum effect can be quite different for different quantum states. Now, again, depending on your UV theory, at the end of the evaporation, you may get different Penrose diagrams, but we will be focusing on the early stage of the evaporation. So for that part, all these proposals actually would look very similar. So we have a single Penrose diagram like this to talk about. You have a symptotic Schwarzschild metric far away from the horizon. And within that regime, within this regime, you may expect something different. So I have a gray shaded area here, which is the neighborhood we should pay attention to. And this is the surface of a collapsing matter. So inside the matter, you may have a metric which is determined by the classical matter. So in this neighborhood, you have a trapping horizon, but it's time-like. I'll explain why it's time-like in the next lecture. But we can show that it's time-like following the assumptions we made in the conventional model. And so observers can go in and out. You can use a single basis of functions for the quantum field theory. So everything is smooth. And we will only talk about physics in this neighborhood. Now we also talk about the assumption about a quantum state. And we assumed it to be uneventful for freely falling observers. And naively, it's a consequence of the equivalence principle. More precisely, if you have a geometry with the characteristic length scale A, the Schwarzschild radius for the Schwarzschild solution, then you expect that the energy momentum tensor of the vacuum for free-falling observers to be no larger than 1/a⁴, according to the equivalence principle. Here, tau and sigma are the local time and radial coordinates for a bunch of freely falling observers. Although here I should make a remark that there is actually an assumption involved in here. I mean, here we already assumed Schwarzschild approximation is a good approximation in order to conclude that the characteristic length scale is A. If we drop the Schwarzschild approximation assumption, then we don't really know what is the characteristic length scale. Okay, so that's why we need both Schwarzschild approximation and an eventful horizon as our assumption. Now, so
excuse me. So in this previous slide, so here, so this amount of energy momentum tensor. So my question is whether this amount ensures correction to this Schwarzschild metric is small enough.
Whether this, sorry, you agree with this line.
So
right?
suppose this is correct, and my question is whether this back reaction to the geometry is small. Is this correct?
That's right. That's right. So I'll show in the next lecture how people checked that this is.
Okay. Thanks. Yeah.
Yeah. Right. So then, in general, if we have a spherically symmetric configuration, the metric can always be written this way, where you have this conformal factor C in front of du dv. U and v are the outgoing and ingoing light cone coordinates. And r squared, this r is the areal radius, and you have the metric for a unit sphere over here. And people have checked that, you know, with this onsets, if the energy momentum tensor for local freely falling observers are like the previous page, then just the change of coordinates tell you that in this coordinate u and v, the energy momentum tensor would be like this. In particular, when you approach to the horizon where c is very small, you see that TUU is very small and TUV is also very small. Only TVV remains as the order of 1/a⁴. So this is what people usually say, that for the conventional model, when you are around the horizon, this TUU, which represents outgoing energy flux, is 0. So you don't see outgoing energy flux. So when you are freely falling through the horizon, you don't feel like outgoing Hawking radiation coming at you at very high energy. There's no such thing. On the other hand, at large distances, you do have Hawking radiation to take away energy from the black hole. So it implies that you have ingoing negative energy. So this TVV being of order 1 over a to the fourth must be negative in order for energy conservation. You have negative energy particles, pseudoparticles. You have negative energy flux ingoing to the horizon, and then positive energy outgoing at large distances. So to conclude this first lecture, what we will do in the next lecture is to go over the conventional model in more detail, and in the last lecture, pointing out some loopholes. But before we do that, we see that there are two possibilities. One possibility is that the conventional model is correct. There's nothing missing. All the calculations are correct, and they are not missing anything. And then that would imply that decoupling principle probably fails, and we need to accept more radical resolution beyond effective field theory. In the other possibility is that conventional model is wrong because it misses something. Maybe it's not the generic case. Maybe it requires fine tuning, or maybe, well, I wouldn't say they made mistakes in calculation. That is very unlikely because a lot of people have repeated the calculation, but maybe they have missed something. There's something they need to check, but they didn't check. But again, the minimal resolution we need is that whenever there is Hawking radiation, there must be high energy events around collapsing matter in order to resolve the information loss paradox. So that's the end of my first lecture. Are there questions?
Thank you for a beautiful story about this review of information loss paradox. So do you have any question to Pei-Ming, if any?
What is your answer?
Hi.
Pei-Ming?
Hi.
Among these two possibilities, what is your preference?
So, of course, in the last lecture, I will point out something missing in the conventional model. So I will show that whenever there is Hawking radiation, there are high energy events around collapsing matter.
So you believe in firewall?
Well, no, that's different, right? So I believe in two possibilities. One is that there is no Hawking radiation and an eventful horizon. The other is Hawking radiation with firewall. So actually what I'll show is that there would be a transition time of scrambling time. After scrambling time, if you assume initially an eventful horizon, after scrambling time, either case will have to happen, either firewall with Hawking radiation or no Hawking radiation and no firewall. And the difference would be determined by the UV theory. Namely, the low energy effective theory will have to break down within scrambling time. And then it's a question of string theory, which case would actually happen? Would there be firewall or Hawking radiation or not?
So in what case there will be no Hawking radiation?
Yeah, if there is no firewall, there is no Hawking. Well, that's, I mean, that's a possibility. Yeah.
So you say that according to what the UV theory is, it could be such that there is no Hawking radiation.
Yeah, that's right.
Maybe you will maybe more later, but it is just curious that in what UV theory there is no Hawking radiation.
Yeah, actually, you can look at the paper by Kawai and Matsuo and Yokokura in 2013, what I call the KMY model paper. In that paper, before they presented their model, they had a section in which they considered a thin wall with the usual formula for vacuum energy momentum tensor. And they did it analytically and numerically, showing that what would happen is that according to these higher derivative formulas, the evolution of the black hole is such that Hawking radiation would appear for a while and then stop. So it's not too hard to get this result, actually.
Oh, I see. Okay. Thank you.
You're welcome.
So that's a great teaser for the second and third lecture.
I want to make sure that people would stay.
Yeah. So one question from me is that in the last line of this slide, you said that the high energy events. And so are you going to discuss this high energy event within the low energy effective theory, or you need to actually add something to it? So what's going to happen for this?
Right. So if we are going to have high energy events, they are not going to show up just, abruptly. So for example, if we are using standard model, which is valid up to say TeV, then before it becomes invalid, at least we will see GeV scale particles, right? So when you have GeV scale particles popping out of vacuum, it's still a reliable theory. So what we're going to see is just that there will be, moderate energy particles coming out before the effective field theory breaks down. So whether there will be Planckian scale particles, that we don't know, that we need high energy theory. But at least in low energy effective theory, there must be some signal, some hint that, oh, your theory is going to break down. You cannot say, well, it suddenly breaks down. That would be like giving up predictivity.
I see. Thank you. So is there other question? Okay, if not, yeah, so let's close this session with applause to Pei-Ming. Thank you very much, Pei-Ming.
Thank you.